So starting with the next chapter in TRO, which is chapter 8, we're going to look at electromagnetic radiation, a really cool subject. And what that deals with is an oscillation, which we typically think of as a wave, that is traveling in some direction, and this wave would have some kind of electric field associated with it, and then perpendicular to that field, and you'll have to forgive my drawing here, there's a magnetic field. And these two are at 90 degrees, and then they they travel in some field or in some way. So there are some things that we can quantify about these kinds of things, one of which is called the wavelength, and that gets the symbol, looks sort of like I say the front half of a giraffe looking sad. So it's called lambda. And lambda represents wavelength, and that is given in units of meters. And so what wavelength represents, if I was to draw a wave right here, looking like this, if I was to take the peak and the peak of the next crest of the wave and the distance between those two, that is the wavelength, and that's what's given in meters. So that's how we measure wavelength, and that's when we talk about the wavelength of light, that's the wavelength we're talking about, the distance between the peaks of two waves or the troughs of two waves. The frequency of the wave has this fancy symbol, looks like a fancy V. It's called nu. And this has units of, well, there's a few different units. Hertz is the one that we use most frequently. Reciprocal seconds, 1/seconds, or seconds to the -1. They're all the same unit, but they're all units of frequency. And so if you were to think of like waves on the ocean sort of traveling past, if you were to stand here watching them, you would count the number of waves that go past you in a certain amount of time. And how many waves go past you in a certain amount of time is its frequency. So this would be like 2 waves moving past you in a second or something like that. That would be a frequency. And then the amplitude is something we don't do a lot of calculations with, but it tells us the amount of displacement here in this wave. So your book talks about it. It's a good thing to know about. It's nothing that we do a lot of calculations with, but it does tell us about the intensity of the wave and how high these waves are. But an important equation comes out of this, and that is that the wavelength, lambda, multiplied by its frequency, nu, will give us a speed. And that's the speed of the wave in whatever area it's moving in. And that kind of makes sense because lambda is given in units of meters, frequency is given in units of 1/seconds, and what that gives us is meters per second, which is totally a speed. And the speed that we're talking about here is the speed of light. So 3.0 times 10 to the 8th meters per second is how fast these waves end up moving. Now, electromagnetic radiation is broken up into various areas. So we're going to want to take a look at them, starting with the low frequency areas. This is the radio portion of the spectrum, so radio waves, and there'll be a PowerPoint on this that you can sort of take a look and see what's going on here. And then moving up a little bit, it would be the microwave portion of the spectrum. You probably have one of these in your house. Moving on up a little bit more is infrared, or often referred to as IR, followed by visible, followed by UV, ultraviolet, and after that is X-ray. And then beyond that, even more, is gamma radiation. And I'm using a symbol there for gamma. So these are the ones that we deal with the most. Invisible, just this little portion right here, that's the only bit that your eyes were ever built to see. So there's a whole lot of light outside of what our eyes are able to see in terms of frequency. And also this is, I should point out, not to scale. But we're going to want to look at the different things that go on in each of these areas. So you're going to want to see the other PowerPoint that I've posted. That will describe what goes on in each of these areas so that you can know a little bit more about these. But you are going to want to know that various, in terms of frequency, the low frequency part of this is radio, the high frequency part of this is X-ray. Now the important thing to realize is that because our relationship looks like this, frequency times wavelength is equal to a constant, that means that they have an inverse relationship. So if frequency and wavelength are on, I'm sorry, I'll put it up here. Frequency and wavelength are on a teeter-totter. If one goes up, like if frequency goes up, the other must go down. Okay, so that means that on the low side for frequency, low frequency radio would be on the high side for wavelength, meaning that the wavelength of radio waves is rather large and the wavelength of X-rays is really small. All right, and again, that would be in the PowerPoint, so you'll want to take a look at that. We can use this to solve a couple of problems, one of which is what is the frequency of 745 nanometer light? So again, here's our equation, lambda times nu equals c, and we're trying to get the frequency. This is a constant, and this is what we're given. So c over lambda is equal to nu, and that's 3.0 times 10 to the 8th meters per second over 745 times 10 to the minus 9 meters. It's meters on top, so it needs to be meters on bottom. So we do a quick conversion of nanometers to meters. Remember, nano means 10 to the minus 9. Run this through our calculator. We should get a relatively high number, 4.03 times 10 to the 14th. And then the units of that is reciprocal seconds or hertz, so that is frequency. And what is the wavelength of 93.1 megahertz light? 93.1 megahertz, that's a frequency on the FM dial for WXRT in Chicago. And so let's figure this one out. So again, lambda times nu is equal to c. So c over nu is lambda. So 3.0 times 10 to the 8th meters per second over 93.1 times 10 to the 6th per second. That's what mega means. It just comes on down here. And then when we run this through our calculator, what we end up getting is 3.22 meters. So it's a rather large wavelength, 3.22 meters for radio waves. So again, a very low frequency for radio waves gives us a very large wavelength. So try to keep that inverse relationship in mind. It's inverse. Okay? Thank you.